Thank you everybody for joining us here today for this Exceed webinar covering sort of a quick introduction to Singularity. This talk is essentially designed for the new user to Singularity and sort of covering what Singularity is and why you might find it useful in your work. So if you're doing some sort of scientific or high performance computing, it might be a valuable tool for you to get familiar with and use in the future for your research. So I'm Marty Candice. I work in the HPC User Services Group here at San Diego Supercomputer Center. I mostly work on Expanse, our latest NSF funded system. So if you have allocations on Expanse, our team helps answer any questions you have about getting your work up and running on our system. So we may have communicated before. If so, good to see you again. If not, feel free to get in touch with us if you have any problems on our systems. Okay, so today, get this. There we go. There's a lot of material you can cover when getting started with Singularity, but I really just want to give a high-level overview of what a container is for those who don't know what a container is. I would say I'm still learning myself exactly how to understand all the bits and pieces of what makes a container, but I'll try to give you what I understand and enough for you to have like sort of a conceptual notion of what a container is. I'll talk about specifically what Singularity is and why it exists and what you can use it for in your work. So any sort of introductory containerization talk gives this analogy with a shipping container. And over the years of giving this talk, I've sort of grown more fond, I guess, of the analogy that's used. And it really does give a sense of what we're trying to do with containerization, right? So most people don't usually probably think about shipping containers very much, but they are sort of a modern invention of the world we live in. We're all a bit more familiar now with supply chain issues and things like that over the last few years, but it's really only in the last 70 years or so that we've sort of had the modern shipping container and the system that's developed around it. And before then, right, individual goods that were shipped from different locations, whether on boats or rail or truck, everything was sort of loaded individually and packaged in their own sort of unique containers, right? And it was all handled by hand for the most part. Maybe at the docks you have cranes and things like that, but everything was sort of individually loaded and handled by people, which made it a little bit more inefficient. You spent a lot of time loading and unloading goods rather than moving the mode of transportation that the goods are being shipped on. Right, so it's sort of this turnaround time leads to some inefficiency. Also, because these are sort of individually handled, they're a little bit more insecure, potential loss of goods in transit, essentially, right? And because of this sort of bespoke, unique way of shipping things, originally, you really only shipped luxury or specialty items long distances, right? Most trade was done locally, other than for specialty things like maybe coffee or spices or things like that, right? Or minerals like gold and things like that, right? So that's if it was more locally available, it was cheaper to keep it nearby, obviously. But after sort of the modern containerization or this new intermodal freight transport system we have, right? You have, instead of a unique set of goods that are just kind of packaged in whatever form they come in, they fit on, a ship of a given size or, in shape. Everybody today, essentially, you have these, I think essentially two sizes of these metal boxes, these shipping containers that we see all around us, right? And that you can pack, if you're a producer of goods, you just pack your goods into the container, then you send it through some sort of shipping company to get to your end consumer of those goods, right? And all you have to do is, you load your own stuff into your container, you lock it up, and you tell the person at the other end how to open it, right? And the shipping company, whether it's a rail or truck or ship, every port or rail yard or trucking company knows how to move these containers on and off of their platforms, right? And everybody has standardized tools, there's standardized sizes, everybody knows how much weight can be put into one of these containers. So it creates this very standard, efficient, secure way to ship goods globally, right? And so that's sort of the modern system that we have now. Now, the question becomes, okay, so I have this analogy of this shipping container system of trying to move any types of goods around in these standard size boxes and put them on any platform we want and get them from point A to point B. Well, in the computing containerization that we're going to talk about now, it's, we're talking really about what you want to do on computing systems, which is you want to move your software onto these systems and run them, right? And that's what the power of containerization is for us. Because if you are an Exceed user, you might have allocations on multiple systems. And if you've been Exceed user for a while, you'll know that every system is a little different. You have to, say, compile your code a little bit differently on each one. And so the power of containerization is you might not have to do that anymore. You might just have to compile it once and you can move it around from one system to another, right? Because, how we put software onto systems has not only changes across systems, right? It's obviously changed across time, right? So back in the day, you'd have, physically have to program your computer with wires, right? A little bit later, there's like magnetic tapes and punch cards in, room-sized computers, back in maybe the 60s or 70s, like in the bottom left here. If you were alive in the 90s, you probably had a desktop that looked something like that on the upper right. And today you can even just order a computer in the cloud from your laptop, right? In each of, at least 3 of these systems probably run Fortran, right? So you can run, like, I'm a Fortran programmer by training. I wrote like my dissertation code in Fortran. And it existed at least in 3 of these eras that we see here depicted, right? So in theory, the code that I wrote could run on, in maybe EC2 on that 90s desktop or on that mainframe back in the 60s or 70s, right? Of course, like the language specification has changed a bit, but essentially, if you think about it, the fundamental core, say, language hasn't changed, so some of the functions I wrote would run, but how I get the software into each of those systems is different, right? Like very different in these cases, right? Physically, 2 are physical, one's just all virtual, right? Okay. Oops. And again, this is kind of what I was saying before, like even today, just trying to get your software onto Exceed systems, it's you probably pretty similar now. If you have your, say, code hosted on GitHub, you'll just clone your repo to one of the systems out on Exceed, whether it's Expanse, Bridges 2, or Stampede 2, and you'll start trying to compile your code. But as you know, if you're a user, you have kind of unique software environments on each system, right? Because teams like ours at SDSC, the HPC Distributed Services Group, right? We sort of curate a software stack of compilers and MPI distributions and other libraries that work well on our system versus might work better than the ones that TAC has on Stampede 2, that might work better for the hardware that they have at that time. Right, and this isn't too important. It's just a simple example of me taking a sample of code that I wrote, trying to compile it on one system, our old system before Expanse Comet versus Stampede 2. And it's literally the same set of commands that I'm running But because the software environments are slightly different, you can immediately tell that just compiling it, just running make after downloading the repository, because of the slight differences in compilers and MPIs, just the output from starting the compilation is different, right? In general, you're hoping it's obviously the end result will still run the same simulation, get the same results, but it's just a simple example of showing that the environments are different, and you just out of the box, just when you start compiling a simple code, you're running into differences, right, on different systems. So this is where containerization or software containers comes in, right? A container is really an abstraction of a few different set of technologies that aim to solve this problem of getting your software to run reliably when it's moved from one sort of software environment or computing environment to another, right? It's trying to eliminate these differences between systems by giving you a way to reproducibly, say, compile and run your software with a sort of encapsulated software environment that you can move around from system to system. And how that's done, this diagram just kind of throws up a few of the key names that if you really want to dig into things a little bit more of how stuff works, it all really relies on some new standard, Linux technologies of C groups and namespaces. Not going to really get into that, but sort of C groups control effectively the computing resources, the number of CPUs, memory, and even network that your sort of container lives in or can use, they can consume. And namespaces are more related to the file system. And so I'll talk a little about that, but each container has its own sort of file system that you are installed. That's where you install your software, but there's other things about interacting with file systems outside the containers and things like that. And I'll talk briefly about that as well later. So the first thing to understand beyond sort of that's the idea of what a container is like, what is a container in practice? And there's really two things that people are talking about when they talk about a container. And the first one is usually the container image. So if someone's talking about a container, they might be talking about the container image, which is a file or set of files that represents that is that set of data constructed in such a way to create that encapsulated environment. So it's usually just all of the software and libraries that you install in this thing, the image, that will run your target application, right? So it's like the operating system libraries, maybe the compiler you want to use, maybe the MPI, maybe if you're using GPUs, like what version of CUDA you want installed in the container. It's everything you need to put in there to support your application that you want to run. And it's, in the case of Singularity, it's a single file, this image, right? On the other side, if a container image is a container at rest, right? It's just data sitting on a disk somewhere that you have. The container process is the other thing people might be talking about if you're working with containers, right? You might have a container that's running. That's your container process. And it's just, a standard Linux process, like any other application you would run on, say, Expanse or Stampy2 or Regis2. If you're familiar with like looking at your code running with top or htop, right? You can see the processes and how many cores you're using, what sort of the CPU load is, the memory usage. When you look at your container running, it'll look exactly the same as that, right? It's just another Linux process that's running. It's just doing so, running your application in that encapsulated environment with that predefined image that you've created. Right. So yeah, the snapshots here are just kind of showing this just looks like a standard Linux Python process in the snapshot here. And in this case, it was, I think, a TensorFlow GPU example. So you can see that there's like a Python process that's just running on the GPU. That's all these snapshots are supposed to show. So that's what a container is. And if you've seen the movie The Matrix, this is kind of my analogy for what a container is to, the supercomputers you're working on. It's really, you can kind of treat it like this loading program, right? You can put anything you want in it. You can bring it to the supercomputer and you can use it, right? So you can bring anything you need, right, to do your research. Now, one of the important questions might come up if you're not familiar with containers is, but you might have heard of virtual machines in the past. Maybe you've used them before. Maybe you've run on Amazon or Azure, their instances there. What's the fundamental difference between a container versus a virtual machine, and sort of why do we use containers on supercomputers, right? And it's really comes down to there's less overhead in running containerized applications versus running the same application in a virtual machine, right? When you're running in a virtual machine, you really do have, in general, this overhead layer of not only the guest operating system that's, your application might be running on there, but you have sort of a virtual layer that's emulating the hardware above the actual physical hardware, right? This hypervisor or hardware layer that's sort of abstracting away, a lot more from the underlying host system and the hardware underneath. Whereas a container is really directly is using the Linux kernel from the host system itself. So it's tied a little bit closer to the underlying physical compute node that you're running on. And so this gives you almost, in general, the same native application performance you would get in the container as you would just compiling it on the system natively itself, right? And that's kind of what the big, one of the primary advantages. Not only do you get this ability to put any software you want into the container, you also don't pay any performance costs. That's why it's kind of very interesting for an HPC user to containerize their application, because essentially it's, if you can move your compiled project from one system to another and never have to recompile it, that sounds pretty awesome. If you just move from system to system and run the same thing, right? And you'll get the same native application performance you would if you compiled it natively using each individual unique environment on each system, right? So in addition to performance, again, you get this freedom to bring your own software environments wherever you want. Nice thing about doing scientific computing, right? Reproducibility is a big challenge. Like, how do you reproduce the same version of your application compiled with the same version of a compiler, the same version of an MPI distribution, the same version of CUDA, run it and get your output? You rely on that output for a certain paper, and you go back another year, try to rerun the same calculation. If you don't have exactly all those same versions anymore and you get slightly different results, that could be a challenge. But if you have sort of a process of containerizing your applications over time throughout the life of a project, you will actually be able to, you might not only have that container image saved so you can rerun exactly the same image, but at least you might also have the manifest that you used to build that container, so you know exactly what versions of software you installed in that container and all the dependencies that you used when you ran those results for that set of research, that set of data that you published. Right? So in addition to the reproducibility, it's just built on open standards. It's just containers run on pretty much any Linux distribution, and again, you get this portability of build once and run almost anywhere. So the almost part I'll talk about in a little bit here. Well, or I'll talk about right now. So the main limitations of containerization are sort of these 2 or 3 points here. The first is it's always going to be dependent upon what type of CPU architecture you're running on. So if you have a container built for an ARM chip, it won't run on an x86 CPU, right? So you'll have to rebuild your container when you move between CPU architectures or GPU architectures and things like that. Portability also is an issue in some cases when you rely on sort of advanced features, such as the most common are, sort of GPUs or, high-speed networks like InfiniBand or something else proprietary that's sort of not standard, right, that you might be working with on a given computer. In those cases, to take advantage of those more advanced capabilities, you have to sort of build into your container some of the libraries or set it up in a certain way that you have this compatibility not only between the libraries in the container have to sort of be compatible with the libraries outside the container on the host system, right? So, and you run into places where operating system kernel numbers and glibc versions start mattering, but the most common are really with the sort of peripheral devices like InfiniBand drivers and GPU drivers and things like that. The last point here is a good or a bad thing. It depends on how you look at it. One thing about containers is, as I mentioned, they have their own file system, right? You are installing stuff into a file system that is inside the container. It represents sort of the environment you're building in there. And so one thing that gets a little confusing to people when they start working with them is, you really do have this file system isolation. You have to, if you want to work with files outside the container, there is a process for sort of poking holes outside the container to different points in, say, on Expanse. You have sort of your project storage on Lustre, you have your Scratch storage on Lustre, you have a local Scratch disk on every compute node. If you want to access those different points on different file systems, you sort of have to just remember to apply some options when you're running your container to see outside the container and touch those files, or allow the container to see those files and access them from the outside, right? Now, if you are familiar with containers, all of you are most likely more familiar with Docker. And so I usually just do a quick comparison of what Docker is, or if you're not familiar. But it's really the most popular container platform today, for the most part, or at least more on the container image side and the type of containers you'll run. And it really provides the same capabilities as you'll get in Singularity. It's really the main difference is it was designed to accommodate more web services. So use network services like running web servers, databases, systems that are always on all the time. It was really more of a transition from, hey, we have these virtual machines doing something similar, but there's this other thing that makes things run a little bit better, right? Moving to containers, so you can kind of get better performance, but we still can just run our web server or database out of there, and it still gives you all the advantages of just like running those things in a virtual machine as you do in a container, but it runs faster, it's more performance, right? And if you're getting into containerization, I definitely would recommend trying Docker. I'm getting a little bit more familiar with it myself right now, actually. And it's easy to install on your laptop at home or on a VM that you might have access to. It's easy to install, it's well documented. There's huge community and a bunch of containers on Docker Hub that you can download and use. The one thing is, when Docker first came out, it really wasn't designed to run on HPC systems, right? Even though you have all these cool advantages of containerization, obviously the scientific computing and HPC user community was very interested in them, but it wasn't really designed to run in these sort of shared resources, nor was it sort of designed for like a batch-based workflow that you're probably used to if you run on Exeed systems, right? It was really designed for this model where the container is going to run kind of like a virtual machine where it's going to be on all the time. And also it was kind of assumed that, it was going to run on a machine that no one else had access to, that, only the system administrator who was running that database would have, well, root access to that VM that it's running on the cloud, or, and you could sort of trust the environment was sort of secure itself. It wasn't designed into Docker's sort of runtime model, the security that you'll see in Singularity. And the last point is, it really wasn't designed for sort of, if you run applications that are sort of tightly coupled and scale out across multiple nodes with MPI, right? It wasn't really designed to run applications that are these sort of highly distributed parallel applications. It was more designed for, running, again, network-centric services or microservices in, in the cloud, or, on someone's sort of infrastructure, for more of a sort of business applications, I would say, right? So that's where Singularity came from, right? That's how Singularity was born. There was enough interest from the scientific and HPC user community, coming to teams like ours at, in this case, it was at Lawrence Berkeley Lab, where they were like, came to sort of the people who were more IT, the scientists and HPC users came and said, hey, what can you guys do? We want Docker, but there is no Docker that you'll let us run. So what happened? So one of the people there, invented the version of Docker that they would run, and that's what's called Singularity, right? So it gives you all the same advantages of containerization, this reproducibility, portable, shareable, distributable containers. But it did two things different. It basically said there's no trust in the security model, right? So basically, you don't have to trust the user to the same degree you did in Docker. And so basically, if you are, well, I'll mention that in a bit, but basically, it's assumed untrusted users running untrusted containers on a system, right? And trying to minimize the damage that someone can cause by some of the other the security flaws that they saw at the time in Docker for running in these HPC shared environments, right? And the second thing is they from the start incorporated, we have to be able to run on HPC hardware with, say, InfiniBand, with GPUs, and run sort of scientific applications, especially, ones that use, say, MPI, right? Those are kind of the things that they needed to support, which weren't really sort of Docker native. Oh, yeah, I forgot. So the last point here. So, of course, so Singularity was so successful in its first few years. The team from Lawrence Berkeley Lab and the other contributors who'd sort of grown up in the Singularity community as it was developing those first few years, there was a company that was formed, Scilabs. So you can definitely click on that link from the slides, or just check out the company's website. It's still up and running. It's been, I think, maybe 3 or 4 years. It's been up and running. So you can sort of, there's now, paid services, Singularity Enterprise, Singularity Pro. There's still a community version, Singularity CE, Community Edition, I think it's called. Yes. And so it's all still open source, but they just are building this, services around the Singularity product. So you'll see this Scilabs is associated with Singularity. Of course, in these ventures of, I guess, trying to make money, things get a little bit complicated. So the founder actually left Scilabs 2 years ago, maybe. Anyway, so there's now going to be a little bit of, I think, turmoil, not turmoil, but as HPC users, I just want to make sure you're aware of, you'll start seeing probably both Singularity and this new version of Singularity Apptainer installed on Exeed systems over time, right? So this is sort of a fork from, well, essentially the two projects have forked. So essentially the community edition that was being maintained by part of the team who was outside the company sort of split off and is now renamed their fork Apptainer. It's now official like Linux Foundation project. So they're sort of developing their own community edition now. And they just came out with, I think, their 1.0 release. And of course, Singularity is still going through Scilabs as well. So right now, everything should be fairly compatible, but over time, these projects may diverge. So I would just say, if you're going to get into using Singularity a lot in your work, just be aware that there's also going to be Apptainer. And how to juggle that is still going to be something we're going to have to figure out over the next couple of years, probably, at least in the HPC space. I assume they're going to exist side by side for some time, because there's going to be different sets of communities who are going to want both, or one or the other, or need at least one. So I assume we're just going to be supporting both for the foreseeable future at some point. But for example, on Expanse, we don't have Apptainer yet. I'm sure we'll have it though in the next year if I had to guess. In addition to Singularity Pro, which we have. Anyway, so Apptainer is Singularity, but it's renamed New. So just keep that in mind. Everything I'll talk about is just Singularity. Everything is basically the same with Apptainer. So I haven't played around with Apptainer yet myself, but they're working on sort of keeping compatibility as close as possible. But I would say there's no guarantee over the long term. Anyway, so the unique features of Singularity are compared to, say, Docker, is, if you're familiar with Docker actually, their container images are sort of built out of a bunch of different layers of files that get assembled when you, say, download the container or run the container, depending on how you look at it. But Singularity is actually just a single file image. So everything gets installed into one file. So you can kind of just run a hash on that, and you'll know that that's that version of that container that you downloaded or built it at one time. Everything is there. It's basically unmodifiable. So everything, once you build the container, it's just there, right? So this is this important part for reproducibility, right? Where in Docker, that would be very difficult to maintain with all these layers and things, because each individual layer can get updated and things like that. Again, the security things. So basically, there's no root daemons, no processes that are running. There's no change of, there's no ability for a user to change from one name to another. Like if you are your username on the system when you run the container, right? Whatever your username is on Expanse, when you look at the username outside the container and inside the container, it's the same. It's owned. All the processes that run are owned by you. So it supports this shared multi-tenant environment that we have, say, on Expanse, where we've used our shared partition, right? Your job will run alongside other user jobs on the same nodes. So you sort of have this shared environment. This is why this security is important. This sort of username level security is important. And of course, again, as I mentioned, it sort of supports all of the HPC hardware that you might want to use and HPC applications that, for example, might use MPI. Now, the most common use cases that we see are for Singularity usage on our systems is, first and foremost, is sort of building and running applications that are hard to compile in our native software environment. So for example, like I maintain a lot of the containers that we sort of build for users out of the box and just have on the system for you to use. And some of them are like things like PyTorch and TensorFlow, because usually those packages themselves are assuming you have like a Ubuntu based operating system, but that's not usually what most supercomputers run. And so it's, having the containers allows us to put a different operating system in the container to support those builds of TensorFlow and PyTorch, and still run it on Expanse, even though now we're running, say, Rocky Linux. So we've actually moved recently from CentOS 8 to Rocky Linux 8, who is actually also being led by the original founder of Singularity, who's on the Aptainer steering committee. Yeah, so that's what I do a lot of my work, so is building sort of applications that we have a difficult time supporting natively in our software module environments. If you've used it, that's one thing. Another thing is, if you are using some sort of commercial or proprietary software where your research group has bought an application or has access to some software. For example, I was helping a user the other day. She had a sort of a genomic instrument in the lab, came with some software that they could run, but it again required an Ubuntu library. I think it was just an installable binary, so it was already compiled. There's nothing for us to compile, but to meet the requirements of the software as stated in the user documentation, right? We had to stick it in a container that met all those requirements, right? That we couldn't necessarily, change the whole system, operating system on Expanse just to support this one application, right? We were able to just put it in a container that supported the version of the software, and it worked out fine. Probably the next most common thing is if you already work with Docker or there's Docker containers that you come across from a collaborator, you can convert Docker containers into Singularity containers, right? So if you're already set up with Docker or know a lot about Docker and you've been building Docker containers, if you want to bring those Docker containers to a system like Expanse, you can just use Singularity to pull those down and convert them, and you're off and running. And so, yeah, this is kind of the standard Singularity workflow. If you sort of get into a habit of using Singularity, to sort of go from building your own containers from scratch to running it on HPC systems that you have access to. The one stumbling block I would say is if you go down this route of building containers natively, and if you've already used Docker, you're probably familiar with this, but the one stumbling block is to build your own containers, you actually generally need a local system where you have root access to, right? And that's not going to be on Expanse. It's not going to be on Stampy2 or any HPC system that you have access to. You will never have root access. So you cannot build your containers on those systems. In Singularity, there are some special features that would allow something like that to happen, but we don't implement it. I don't know if anybody else on the Exceed network set of systems does, but in general, this is the rule. You have to sort of build your containers somewhere where you have root access to. So for example, you can do it on your personal computer or your laptop. I use Jetstream in Exceed. So if you have an allocation on Jetstream, you can spin up your own VM, kind of like EC2 on Amazon. And off you can go install Singularity, build your containers there. Right. So once you build your containers, though, you just transfer them to the systems you have, and every system in Exceed has Singularity. Many systems, I mean, I'd be surprised if there wasn't an HPC center that didn't have Singularity. So, but that's if your home institution doesn't have Singularity, that's on your local cluster. You might want to talk to your system admin. It's a useful tool to have. So if you are interested in getting more into trying Singularity, right, it is Linux only. Okay, you might see out there at some point there was a Mac alpha version. I doubt is still being pursued by the company by Scilabs. But if you really do want to get into it, one easy way, if you don't have access to say Jetstream or a VM or don't have a Linux operating system on your own, say obviously if you have a Mac or Windows, I have VirtualBox running on my Mac, so you can just spin up a virtual machine on your laptop. You can install Ubuntu or CentOS, Fedora, Red Hat virtual machine, whatever, and you can install Singularity and build and test your containers there before transferring them over to say Expanse or any other system that you might want to run on. Right? It's not that hard. It's just it gets a little you have to if you've never used VirtualBox, you have to jump through all the steps of now learning another tool, right? So now you're learning how to set up your own virtual machines on your laptop as well, in addition to then building containers within that virtual machine, right? It's kind of this layers of inception into the virtualization world. But yeah, it's definitely one way to go. I guess I'll mention it in a few slides. There's another way you can go, but when you do get started with Singularity, these are really the three commands that you need to learn how to use. So if you're going to build your own containers, you need to learn how to use the build command, right? So there's different ways to build your container images. There's, you can build it from scratch using what's known as a definition file. So if you're familiar with Docker, this is like your Docker file. It's literally just a list of all the stuff you want to install, essentially. And there's other sections and things you can do things with, but that's kind of all I use it for. But you can also, again, as I mentioned, you can download any existing Singularity container from any sort of repository, or I guess in container land, it's usually a registry that might, like Docker Hub. You can also download Docker containers, convert them to Singularity containers. So the first, if you're gonna do anything with containers with Singularity, you'll definitely need to learn the build command. Second is the shell command. This just allows you to get like an interactive shell into the container and poke around. It's pretty useful, especially when you're doing the development of, say, your own containers, because you'll log in, it's like, oh, that package didn't get installed, or that thing didn't finish compiling correctly for some reason. And you have to go poke around and see if, what happened. Maybe there's an error log or something in there. And then the last one is the most important when you're running a container. It's just the exec command. So this is the command you'll use to run a container, or run a command inside the containerized environment. Right? And I think we check the time. So we have about 15 minutes left. And so this is kind of where I'm going to stop and maybe just try to do a demo, answer some questions. But again, I had one other slide that I've updated, and I checked on something for you guys. Is if you don't want to go the route of, say, installing Singularity in VirtualBox on your laptop to build containers and play with them, starting out, you can also, and so this is the process, just, use the first Singularity build command. You just build your container, this .cif file from a definition file, which is this manifest that I mentioned. And if you have a manifest of the things you want in the container, this Singularity definition file, in addition to building it natively in a Linux environment with Singularity installed, like you have here in these screenshots, I'll come back to that. There is the Scilab's Cloud Remote Build Service. So I think you can get a free account there, and you get up to 11 gigabytes of storage. And so this actually will allow you to write a definition file for your container, send it up to the cloud, and the service there will build it for you and store the container there, and you can download it to, say, Expanse. I don't have a demo for that, but I did want to point out this is still open and public, I think, and you get, it used to be 10 gigabytes, but now it looks like it's 11. So this is another way to get started with building your own containers and just, say, downloading them to Expanse and trying them out. I think I hear someone asking a question. Okay, I thought I heard the mic come off. Okay, so let me try to answer some questions. I don't know, where do I start?
Already get started, Dimitri. His is the first one that's on the list.
Yeah. Oh, okay, so yeah, let me do a few questions. So AppTainer will be the free one. So AppTainer will be, I believe. Yeah, I mean, AppTainer is open source, kind of free software for, Linux Foundation wise. There may be people who spend products off of that. I don't know. But the Scilab's Community Edition CE version is also free and open source, and you can use that. I mean, that's what I use still. I haven't, like, as I mentioned, I haven't used AppTainer yet, but there's certain things that, like, right now, I think you can still sort of yum install Singularity into a CentOS, at least 7 operating system from the Apple repository, if you know what that is. And but the problem is, like, the person who was maintaining that is now in the Apptainer team, so I don't know if Scilabs is going to keep their own Singularity RPM up there to get installed, and because I know there's already an Apptainer RPM from the previous maintainer of the Singularity one, so it's going to get a little complicated, but that's kind of how things are right now. But yeah, they're both open source. All the community editions, it's in Apptainer, they're basically the same right now. It's just mostly variable names that have changed in the code and in the documentation. That's about it. So Drew Lee says, yes, Singularity Pro 3.5 was removed from Expanse. 3, 7, and 9 are now added. Yes. What is our policy as to removal of old modules? Is there a channel that users can receive notifications or plan on changes like this? We generally do not publish changes to the software of the software stack, but yeah, in this case, I mean, you're the second person who asked for something like this, so maybe we'll consider something like this in the future, some sort of way of notifying people. I mean, one of the things is, right, this these changes were supposed to go into effect when we had the system down maintenance to upgrade the whole operating system 2-3 weeks ago now. So they were supposed to change then, when basically all of the underlying software, at least operating system wide, changes. So we did kind of tell people things were changing a lot. But yeah, I mean, individual packages, maybe we can publish a change list at some point. I don't know. We don't have anything like that in place though. Anna asks, how do you convert Docker from Singularity? I'll show you that in a second. I just want to get through a few more questions and I'll do a quick demo. But maybe that's where I'll start. Does Exceed provide, so Maggie asks, does Exceed provide support to users for help with building these containers, like examples? Yeah, I mean, so what you would do is submit a ticket to, if you're an Exceed user, right, you have the access to your Exceed user portal account through the Exceed user portal. Just submit a ticket there, and you want help running your software on whatever system. And I like, for example, yeah, I mean, that ticket, basically that same kind of questions, like, that user asked, like, hey, I have the software I want to run. We looked at like what the requirements were, like, well, there's no way we can run this just on the system as is. We have to put it in a container. So we helped put together the container for her and her research group. So yeah, I mean, it's just like asking Exceed for any other sort of software support on the system, whether or not different sites have enough people to help build containers for you. I don't know what their policy is. We do. So we help you put together containers if it's needed, right? If it's not needed, we'll tell you. But if, for example, it's usually like a one-time kind of deal, though, right? If you want to sort of start maintaining your research code in your labs, like projects in containers, like, we'll help you build like the first one, but you're gonna have to like sort of maintain it yourself over time. So yeah, that's kind of what I would say.
Hey, Marty.
Yes.
Marty, I think these are great questions, folks, and I'd like you to move to the demo because we're getting kind of late in the hour, and then
Sure.
we can hang around and answer more questions if folks still have them.
Okay, yeah, let me go ahead and jump out of the talk here. And so yeah, these slides will be posted. So there's a few other ones you can look at. I'm still trying to update it, a few things. They're a bit outdated. Okay, so the demo. Let's go to, whose question was it? It was Anna's question. So yeah, I have actually a good demo ready to go. I think I have. Let me just pull up a piece of code I have. So one thing, if you run Jupyter Notebooks on Expanse, we have a way to help you do that. And one of the examples in this, you can actually use Singularity containers to run your Jupyter notebooks as well. So I'm just going to use this example here. I'm just going to log on to Expanse. And if you find a container, say on Docker Hub, that you want to use, or you have it in some private, say GitLab registry somewhere, it's very easy to download and convert your Docker container into Singularity. On Expanse, all you do is module load Singularity. As somebody mentioned, we have 2 versions now. The default is actually 3.9. And in this case, in this example here that I have, I'm downloading this R Jupyter Notebook container that the Jupyter project maintains. They sort of have a set of containers that are pretty standard. There's probably like an Anaconda one. This is just an R environment that you might want to run on Expanse with sort of all the most popular packages, and you can just download the latest one. They have these published on Docker Hub. And so there's 2 ways actually to do this. There's the traditional command is Singularity pull. Docker is just basically you want to pull a Docker container. But the real command, or sort of the canonical command now, is really build. Oops. Sorry. Oh, I forgot. If you use the build command, I forgot you have to change it. So I'm just going to do R notebook.sif, right? So the build command is always Singularity build, the name of the container image you want, and then the source of that container. In this case, instead of the source being a definition file, sort of your custom manifest of things you want installed, this is just your Docker container that's going to get downloaded. Oh, okay. All of our new things are messing me up. Okay, so one thing, if you're an Expanse user after the update, we also put limits on what you can do on the login nodes. So I'm going to spin up a interactive session and try that again. There we go. So yeah, if you're a regular Expanse user, if you start doing things you used to do on the login nodes, and it sort of just errors out or gives you something about threads or memory running out, it's probably, we put these limits of how many resources you can use on the login node. So now you have to, whatever you were doing before that used to work, just go to an interactive session on, say, the debug nodes, and it'll run fine there. Anyway, so that's how you would download and build a Docker container on Expanse. And I'll let that run. I have a few other things I wanted to mention. The other example I was going to run is, I do have a repo of all of our sort of definition files that we maintain on Expanse. Show you those. If you're interested in just looking at what containers we already have, for example, I would say, I mentioned TensorFlow and PyTorch. They're located in this area, in the CM shared apps, containers, Singularity. And you can see a list of things that we have there. So one very popular one I think recently has been AlphaFold. We get a lot of requests for AlphaFold now. But those are a few that we have sitting around right now in this location. So, and if you wanted to have an example, let me just make a quick demo here. So if you want like a quick example of running a container, you can find in the CM shared examples SDSC directory, I'll do the PyTorch one. right? As I mentioned, we only really support PyTorch and TensorFlow through containers right now. And so there's a PyTorch example that you can run, right? I'll show you just kind of what that looks like. Again, it just looks like a standard batch job here. I'm going to have to update the example to say Singularity Pro 3.9, because that's the new module. And this is what a Singularity exec command looks like, right? So you have Singularity exec. The next thing is there's some options thrown there. I'll come back to those. Then after that, there's the path to the image that you're actually going to run. So your container image. Like this is pointing to which version of PyTorch and that I wanted to run. And then you run the command that you want to run inside that container. So in this case, it's Python 3 with this pointing to this script, which just runs a simple MNIST example training demo, essentially. Now, as I mentioned, when you're running containers, right, there's a few other like nuances you have to keep in mind. In this case, there's two options shown in this example where you see this bind/expanse/scratch. This bind mounting option, which you can look at in the Singularity documentation, right, is all it's saying is allow the container to see those file system locations, right? Because what's in /expanse, well, that your project storage and your Lustre project and Lustre Scratch storage are under that sort of top level directory. And then the /scratch is the local hard disk you have access to when you're running on a compute node, right? Whether a GPU or a standard compute node. The second option here has to do with in this case, it's a GPU example. So I'm trying to run this MNIST training example on one of our GPUs, right? In the GPU shared partition. And one thing that's nice, at least with Singularity, is they sort of solve this problem I mentioned of like having to install certain versions of the drivers and things into the container by allowing this -- say NV option. It actually imports the drivers from the underlying host system for the container to use. And it does it in a correct way where you don't have to sort of tie your container to the exact driver matching inside and outside the container anymore. So that's what this is here. So it's definitely, if you're running GPUs, there's like this extra option that you want to throw onto your container as well to get access to the GPUs. And I think we're out of time. So I'll stop there and stick around for questions. There's a lot to learn here, but if you're interested, feel free to reach out and ask any additional questions at any other time. Okay. Let's see, let me get back to these questions. Okay. We left off here. So yeah, Dan mentioned if you're a Windows user, Windows does have the Linux subsystem now. I don't know I've never tried it, but I'd be curious if it works. It sounds like there's a blog post that it might. So if you have a Windows, and I always encourage Windows users to try the Linux subsystem because it's much easier to help them on their end with that stuff, because I'm not a Windows user. The next question from Sagnik, how to transport containers in this context? I don't quite understand the question. Maybe it's how to transfer containers from system to system. I mean, if the question is how do you transfer containers from system to system, well, in this case, while the container is still building, I just sort of downloaded. There's some sort of protocol in the back end. I think it's just probably some HTTP call to Docker Hub that downloaded the container here. So it's sort of just transferring the data for me. I don't know much about the internals there, but if you're just transferring containers from system to system, you can use any method that you use to transfer data around from system to system, whether it's SCP, FTP, Globus. If it's bigger, Globus is obviously the right way to go. Is there a public? Next question is from Drew again. Is there a public Singularity hub like Docker Hub? There used to be, and it was called Singularity Hub, but it doesn't exist anymore. You can still pull containers from there. There's a sort of static cache of all the containers that were built there. It existed for a few years, but the person who used to maintain it left, and there wasn't anyone to maintain it anymore. She went on to a new job. So I'm hoping, I think there might be something like that in the works long term. I don't know for sure, but I keep seeing people sort of talk about it, but not that I'm aware of. I mean, of course, obviously Scilabs has their remote builder service, but I think you have to get more storage. I think you have to become a Singularity Enterprise user. So you have 10 or 11 gigabytes for free, but that's the only one that I'm aware of. Well, actually, that's not true. So you can now create, you can publish Singularity containers now to, at least I know, Azure's container service and GitHub's container service. So if you go to my GitHub, I actually been starting to publish all of the containers that I'm building to there. The storage is free, so it's better than maybe the Scilabs deal right now. I don't know how long that's going to last, but as long as your containers are public, you can publish them here, and they kind of look like Docker images, but they're not quite. It uses a different protocol. If you are curious, it's like the ORAS. So it's kind of, it's the OCI registry as a storage service. So Singularity supports this new standard, and so does, I think it came out of Azure, that's why it's there. Anyway, so there are other options actually. There's just not, what I would say, there's not the remote builder service that used to exist with Singularity Hub. Singularity Hub used to have its own build service. Okay. I think I already answered a question about Windows subsystem for Linux, maybe, I don't know. Nathan asks, how significant is the performance impact of running an application in Singularity container versus natively? Nothing in particular. It's a good question about the map folders. I don't know about that with Singularity specifically. But in general, there's been plenty of studies on running applications in containers versus natively, and if there's, on the downside, there's maybe 1% or 2% difference in some cases, but in general, it's basically no difference for most applications. It's really going to be application performance and maybe, like as you mentioned here, in cases of different IO files. Well, when you start talking about IO, you're dealing with file systems that live outside the container anyway, so there's always going to be some unique things that maybe happen there. But in general, applications as compared as fairly as possible across each other, there's usually very little difference in performance. In some cases, I know in some of these talks that I've seen or papers, you actually sometimes get a speed up by putting your application in the container, because basically the container just gets loaded into memory as one big chunk, and that sort of helps somehow for some applications. Anyway, let's see. Fabian asks, is it possible to run an existing container on Mac OS without the VM? No. I mean, as I mentioned, I think on Mac OS there used to be like an alpha version of a Singularity sort of desktop application, but I don't believe it exists anymore. And I probably wouldn't recommend you try it out. It's probably way too old and insecure. Can a container have 2 different Python versions? Yeah, sort of. I mean, it's no different than installing, say, for example, in some of the containers that we have, say, for example, the PyTorch container that we use Anaconda inside the container to create sort of the software environment, right? Because that's what PyTorch sort of recommends, to sort of build up the software around when you want to compile PyTorch from source. And so in theory, right, you could just create 2 different, say, Conda environments inside a container and switch between them. That might be, I haven't done that, it might be a little bit tricky, but it's probably doable. I used to run, have Python 2 and Python 3 in the same container. Like I used to have both TensorFlow for Python 2 and Python 3 alongside each other, but yeah, so it is possible. I guess it depends what you really want to do with two different versions of Python in the same container. Alep says, can you explain how Singularity exec works with local file structure? That is, say, Singular container is in home directory was considered inside container versus outside the container given its location in the file system. Sure. Yeah, we can just look at the example here, right? So the R notebook container is done. I'm just in my home directory. I have just my, all the files and directories in my home directory right now. And I mentioned before, one of the other important commands is Singularity shell. So if you just want to like log into the container and poke around, we can log in and poke around and see what's here, right? So in this case, we should have, okay. There's a new issue with Singularity on our systems. Just do that again. I'm going to just do this a little different. So I'm using an extra flag here to not import the environment into the container. So by default, at least right now with the new version of Singularity, there's some environment variables getting shipped into the container from the outside that kind of cause an issue when I run this command. So we can see here, for example, to your question though, Alep, I log into the container. I'm saying, okay, I know there's a version of R somewhere in here, so I'm just trying to find out where it is. We can see here that they installed it in the opt directory, right? And actually using a Conda environment, right? So Conda should be somewhere around here too, right? So there's a version of Conda in here that they used to install R, which we have our container does the same thing, I think. So anyway, so you're asking though about the file systems. By default, Singularity bind mounts your container into, or your home directory into the container. So if there's one part of the external file system that's imported into a container for you by default, it's your home directory. So if I run an ls, we see my files in my home directory outside the container up here are the same as the ones inside the container down here, right? So there really is this hole that we've poked out to the home directory, but that happens by default. But if you're familiar with Expanse, I mentioned you have an Expanse, Lustre, projects, storage, my project name is this, or my project allocation is that. But I don't have it inside the container, right? If I look at the same location when I log out of the container, there's definitely stuff there. I have to poke the hole to the outside world through the container if I want to see that part of the external file system and have access to it while I'm running my application, right? So that's this bind mount flag that I mentioned where I have, say, /expanse and I had /scratch, right? So now if I go back and run ls, I can now see outside the container into my Expanse Lustre project storage. Or since I also used this the /scratch, I can also see the scratch mcanvas job directory for the job that I actually have that's running, right? This local file, this local directory where I can use for temporary storage. Okay, let's see. All right, I think, are we almost done? Is there anything I missed, people?
There is.
Marty
Okay.
Ravindar wanted to know if there's a toy example with instructions to create a container on Expanse. If you don't already have that, I think that would be nice to set up.
Yeah, we can try to set them. I mean, the only way you can do that is really to download one, like I did with the pulling a Docker container down, right? You can't build your own container on Expanse. That's one of the fundamental stumbling blocks of people getting started, sort of building their own containers, right? You have to have sort of root access to a system and have Singularity installed. And yeah, I mean, so there isn't a way for you actually to build a container from scratch on Expanse, right? Unless you're just downloading a container from, say, GitHub or Docker Hub or say the Azure Container Registry. Let's see, and as with Singularity 364, I don't have. Yeah, I don't know what the reference, Anna, is to Singularity 364. But if you're trying to run this command, one of the things that you have to change is you have to put your own account into that, in the command, right? This ABC123 is just kind of a dummy account, right? For example, my allocation on Expanse was use 300, so that's what I would put there.
I have another meeting that's going on at 1 o'clock.
Yeah. Okay, Ravinder asks, all right, maybe this will be our last question then, and we'll wrap up. You had mentioned that we can create containers for our scientific applications, run them on Expanse, so the containers would need to be created on our own home machines. Yes, I mean, so essentially you have to come up with some scheme yourself to build your own containers from scratch. As I mentioned, you can, install, say, VirtualBox. For example, I have a Mutu virtual machine running on my Mac right here. So you can install VirtualBox, install Singularity in that virtual machine and build your container there, and then transfer it up to, say, Expanse and run it there. Again, I mentioned you have the Scilabs remote build service. You can try that to build your container. Those are like the two easiest things to do. You can also, if you have access, I mentioned, to Jetstream, I have virtual machines running on Jetstream that I can build containers on there because I get root access to those virtual machines. That's the real key thing. You just need root access somewhere. So if you have like a Linux laptop already set up, you're pretty good to go. You can just install Singularity and get going. But most people don't. That's the problem, right? So, but if you're a Windows user, it sounds like someone said there's a blog post that alleges the Windows Linux subsystem might work. So I don't know, but it's kind of an adventure probably to try. And okay, last quick question. Jacob has asked, is CIF the same as S image? Yeah, I need to change a few of my slides. I think the S image is kind of the older container image format. The .cif is the new format for the Singularity containers. So .cif is just the newer image format. All right. Well, I think that's it. So thank you everybody who stuck around. A lot of good questions. Like, I think this is the most questions we've ever had during this talk, so that's good. Anyway, yeah, if you have any further questions about Singularity, you can just find my email pretty easily, or just send a ticket in to, if you're an Expanse user, through the Exceed user portal, and we'll help you out.